In this session, we're going to look at computational thinking as a specific thinking skill. Now, it's a little bit different to most of the other areas that you've been learning about in your preparation to become a teacher. Most subject matter you've learned yourself when you went through schooling. Computational thinking is not like that. So you're going to be learning not just about how to teach computational thinking, but you need to learn about computational thinking itself. Now, in this course, we've only got an opportunity to introduce you to what computational thinking is. And as you become a teacher and as you engage with teaching of the technologies learning area, you will need to develop a greater understanding of computational thinking, just as over time you'll need to develop a greater understanding of programming and of data systems. Yes, unfortunately, there is only so much capacity in your teacher education program, and the focus is on teaching you how to teach the subject matter, not about the subject matter itself. So we do our best in the time that we have available, but there'll be more time you'll need to spend as you develop as a teacher in understanding computational thinking and in programming and in data systems and all the rest related to digital technologies in particular. But let's start looking at this concept of computational thinking. Now, to make it a little bit easier to frame, broken into four main areas: problem thinking, data thinking, algorithmic thinking, and evaluative thinking. Now, computational thinking is still something quite new. And how the curriculum addresses it is different depending upon what country you're in. So Australia has framed computational thinking in a fairly pragmatic way, looking at a mix of a whole lot of ideas around computational thinking and essentially setting it out as a set of skills that students need to be able to develop and demonstrate around their engagement with digital technologies in particular. But there are some fundamental aspects of computational thinking that we will explore. So, first off, in framing computational thinking, beyond just a set of skills, it's really a way of looking at the world and understanding the world. And if we have a deep understanding of technology and how technology is used and how it works, we can approach the problems in the world in ways that those that don't have that deep understanding don't have the capacity to do so. They don't have the capacity to computationally think. So in digital technologies and in the technologies learning area, we want to develop students' ability to think in various ways that we call computational thinking. Now, computational thinking was originally conceived of as a concept by Seymour Papert. And he was looking at mathematics education and how children can utilize various technological tools, such as a computer or a robotic device, and take control very much of their own learning. By manipulating the computer or these robotic tools, they would learn about concepts in mathematics. But it was the children that were in charge of the learning process that made it particularly special and framed his understanding of computational thinking. So let's hear a little bit from Seymour.
This is an attempt to make a sketch of what a school of the future might be like. Now, nobody really knows what the future will be like, but we know what it won't be like. We know it won't be lots of children sitting in desks with pencil and paper writing all the day. We know that these new technologies, these computers, will be an important part of it. If you go into any school or any home, you'll find many pencils, many crayons, many paintbrushes, because these are instruments that people have made part of their lives. They use the pencil whenever they have a need for it, to draw, to write a story, to calculate. And so with the computer. It's the natural instrument for doing mathematics, for music, for 100 other things. And our goal here is to make it sufficiently part of the culture of the place that everybody uses it when it's needed. There are many aspects to what goes on in the school. We see children here writing stories. In other parts of the school, we see music, we see very special projects like Lego Logo. This might sound like playing with toys, but that's just what's so clever about it. They are playing with toys in a very sophisticated way. The Lego Logo project is one in which children build with the construction set Lego and then interface their constructions with computers so that they can control them. The children are learning to program. They're learning important ideas about motion, about feedback. They're learning principles of engineering design. Above all, they're learning that knowledge is a unified thing and that the scientific and formal and mathematical knowledge is not something separate from their passion for toys, from the things they did since they were small children before they even came to school.
So if you want to learn some more about Papert's work, I've included a link to his text, Mindstorms, and it was actually his ideas were used as foundational conceptions for the Lego robotics kits that were developed in the 60s and 70s and were then used for many, many years since. So I encourage you to explore more of Papert's work and to see where the concept of computational thinking was first developed. So that's just another picture of his turtle robots that were used for many, many years, and his text. So beyond computational thinking, then we break it into a range of different aspects. And the first of these is problem thinking. So generally in teaching, we tend to give students problems to do, and they then set out dutifully to find the solution. And they'll then either get a gold star or a mark on their exam or whatever. We then reward them for finding the solution that we want them to find. But rarely do we allow students to explore problems, to actually set the problem that is to be solved. That's sort of reserved for the teacher's domain to use. So allowing students to actually come up with the problems and explore what problems exist and how they might be solved with technology or with design and technology is an important skill in itself, because that's what they're going to need to do throughout their lives. They're not going to be given specific problems throughout their lives that they have to go away and solve. They're going to be faced with challenges in the workforce, in their social lives, throughout society, where they have to understand the problem and then work out how to solve it. That if we don't allow them to engage with understanding problems and working out what problems need to be solved, then they're going to be at a disadvantage. It becomes a computational thinking skill for them to be able to engage at that level. So problem solving is fundamentally part of critical thinking. And it involves students discovering and analyzing a problem, and then generally finding the best possible solution to overcome the obstacles related to that problem. Now, it involves them defining that problem precisely. And one of the big parts of computational thinking is being able to specify a problem, really clearly and precisely identify what's going to be involved in coming up with the solution, breaking the problem down into manageable stages, which we're going to call decomposition and explore that in a moment. But it's that precise and clear definition and the requirements that are going to be involved to solve it that is a really fundamental skill that students need to develop around their problem thinking. And if we only ever give students problems to solve, we deny them the opportunity to develop that capability. So generally, we have the problem-solving cycle, where we start with students identifying the problem, identifying the causes of why it's a problem, brainstorming various solutions, selecting the best solution, implementing a solution plan, following up, evaluating and monitoring the progress, and then continuing back around that cycle. And you'll see that this is very much the design cycle that we've already looked at in design and technologies. It's a fundamental problem-solving cycle. At minimum, it has 3 steps: identifying the problem, creating a solution, evaluating the success of that solution. But there are various other versions of that, and this is one that has 6 steps. But there are some that have 12 steps or 4 steps. It just depends upon the model and how it's been presented. Okay, so one of the first steps in problem solving is identifying and understanding the problem to be solved. And we use 2 specific computational thinking skills to assist with this. The first is abstraction, and the second is decomposition. So one of the key aspects of problem solving is that there's not one correct solution. And this is something that we don't do well in education. We tend to frame problems that lead to a single correct solution. Of course, it makes it easier for us as a teacher to then mark it and say, yes, you got it correct, or you didn't get it correct. That's almost never the case in the real world. There are always a range of different possible solutions, some better, some worse, and they have various trade-offs. And students need to understand that. They're never going to come out into the world beyond school. I don't like saying that the school isn't the real world. For students, it is the real world. They're problem solving and engaging with life at school all the time. It's part of the real world. But once they leave school and teachers are no longer framing problems for them that have one specific solution, if they go out thinking that there's always that one specific solution to find, that's going to put them at a huge disadvantage. One big disadvantage is when they come to work in teams and they say, no, this is the one solution that I've worked out that we have to find, ignoring the fact that other team members may have come up with other possible solutions that are equally valid and equally effective in solving the problem. So there needs to be that understanding of multiple solutions to any problem. Now, one way that we can explore that is by a process called decomposition. This is where we break complex problems into manageable parts. Particularly for young children, we often start with we give young children really simple problems to solve that often don't require decomposition. But any real world problem generally has a lot of complexity. And starting off to try to solve that is really difficult. If I was to say to you, okay, I want you to create a computer simulation for a racing car game, so students can learn how to drive and race a car around a computerized racing track. Now that's quite a complex problem. It's reasonably difficult. What we can do, though, is start with a process of decomposition. So let's start with being able to move our mouse that makes a picture on the screen move left or right, depending upon if we move the mouse left or right. Now that's a much simpler task to try to achieve, but it's a fundamental aspect of any driving simulation. We're moving an object on the screen. Then the next part of the problem might be to have objects on the screen move left and right, depending upon how the race track is moving past. And again, a much simpler problem to try to get our heads around and approach solving than if we just looked at creating a driving simulator. So breaking a problem down into bits that are small enough that we can understand and work out how to solve is what decomposition involves. And generally, as we solve more and more of these bits, we eventually then get to synthesize them back together into a complete solution. But we can't just start by trying to tackle the whole problem as one. We have to break it into lots of smaller, manageable problems that we can then achieve and then put them back together into the overall solution. So it's related to systems thinking, where we look at how various parts of a system interact with one another, and then we take those little bits of a system out and explore them on their own. Decomposition involves the same sort of process. We break the system, in this case the problem, up into various elements and solve each of those different elements one by one. So there's the old joke, how do you eat an elephant? And the answer is, one mouthful at a time. Even though it's a huge, big challenge, if we start small and just work on little bits at a time, eventually we overcome the whole problem. Now, the next concept is related to this, but this is called abstraction. Now, this is the idea where we can reduce the complexity of a really complex problem by hiding, or I'll say the word summarizing, but we abstract various elements of it. So we hide the detail, so it allows us to focus on bits at a time while still seeing the big picture. So one of the approaches we do use for this is called the ladder of abstraction. So at the most abstract, we have the idea of humans, which contain all of humanity. Then we have subsets of that set of humanity. Artists are a subset of humans. Musicians are a subset of artists. Guitarists are a subset of musicians. Rock guitarists are a subset of guitarists. And the rock guitarist Jerry Garcia is a subset of all the rock guitarists. And he would be the most concrete, whereas humans would be the most abstract. And so we can move from concrete to abstract and from abstract to concrete. And it allows us to get a better understanding of things. So an example would be if we try to solve a problem, let's say we want to solve a problem for creating an object to move from our hand out the window. And the window is 20 meters away, a bit far than we can throw. So that's sort of a relatively abstract problem. We can then make it more concrete by saying, okay, we're going to use a paper plane to move an object out the window. So there could be other ways of moving objects out the window in terms of a set of objects for moving an object out the window. We could make a catapult, we could make a slingshot, we could make a cannon. There could be a range of different ways of achieving that. But we've now made it more concrete by specifying that it's going to be a paper plane. And then we could make it more concrete still by saying, okay, we're going to make a paper plane out of one sheet of paper folded into a dart shape, and we're going to apply so much force to fly the plane. And we can continue specifying more and more detail, making it more and more concrete so that we come to just one possible solution. And it could be most concrete when we say we're going to take this single sheet of paper, that there's no other single sheet of paper that is involved. It's this specific sheet of paper that's going to be folded by myself to make it into this specific shape, so that there's only one single paper plane that is that exact paper plane that's going to be used to do that particular task. So abstraction is where we make things more generalizable. So I could say, actually, let's look at a few more examples first. So now there's an opportunity for you to do an activity on the course website to rank from most abstract to most concrete the Harry Potter books. So take a quick break and try out that activity. Okay, so hopefully you've had a chance to try out that little quiz and see how books can be incorporated into this idea of concrete and abstract. So in this example, the most concrete is my personal copy of To Kill a Mockingbird. It is my physical copy. It's got my name stamped in it. It's the only copy that I own. It's unique. but it is part of a set of all the books of To Kill a Mockingbird, of which there are millions throughout the world. And all of those books are part of a set of prize-winning novels that involve lots of different authors and books. And all those prize-winning novels are part of a larger set, a more abstract set of novels. And novels are part of a more abstract set of books, which are a part of a more abstract set of publications, which are part of a more abstract set of information sources. So what does all this mean in terms of problem solving and computational thinking? It's important for us to understand that many, many things can be abstracted, not just books or physical objects. In this case, we're abstracting an image, going from a telescope to more and more simplification to an icon of a telescope, which could represent many different representations of a telescope that was done in more detail. But of course, because we've taken the fundamental bits that make up a telescope image, the fact that it's got some legs, it's got some sort of tube, the tube is somewhat conar in terms of it's a cone, larger at one end, smaller at the other end. By identifying the fundamental things that make an image a telescope image and simplifying that more and more, we can abstract it. So we're simplifying. We're taking away the detail, but we're keeping the fundamental essence. Now, this can also apply to things such as maps or infographics. In this case, this is a way of representing a journey from the northern part of the Gold Coast to the southern part of the Gold Coast and the various points that will be passed through if you traveled on the tram from the northernmost tram station to currently the southernmost tram station. So again, it's an abstraction. It's not like the real life tram journey. If I was to go and take photos of the real life tram journey, it would look quite different. But we've taken all of that detail of the real journey and simplified it down so that we still keep the essence of it. There is still a lot of information contained in this abstraction about that journey, but it is much simplified. And once we simplify things, we can then more readily work with them and problem solve with them. So other aspects of abstraction are taking this idea of transport links even further, and these are more traditional rail maps of the tram line on the Gold Coast and the Greater Brisbane rail network system. Again, an abstraction, even from more detailed maps. And if we look at some more detailed maps, these are other ones of the same sort of area on the Gold Coast, where one has more labels and indications of contour lines and so forth, giving more and more detail about elevation and so forth of the terrain. The other one is more visually orientated, showing a photograph overlaid with some more information that we can then see where the vegetation and buildings are. But they are again still abstractions of the real world. If we were to go out and walk that pathway, it would still be different. It would be much more complex. We'd have more information, but we would still have a problem in that if we were trying to work out, say, the best way of going and following the tram route, if we were to walk it on our own without a map, that would be much more difficult. Having a map that indicates the direction to travel, the main points that we would see, the labels of different locations that we might need to reach or not reach, provide us with more information than even the real world can through a process of abstraction. So when we take this into computational thinking, we can relate it to some of the programming that we've already looked at. Now, at the top of this diagram, we have what's called a visual programming language. This is where we put together some blocks. There's a starting block, which is a little starting flag, and a red block meaning ending. And then along the way it says move forward 10, move back 10, and do that 4 times. But there's no text involved. It's been abstracted to where there's only some numbers and some shapes that give us the information of what's to occur in the programming language. Slightly more concrete is the next one that you're more familiar with, which is block-based programming, where we've got some text giving some instructions of what to do and some numbers about quantifying how much is to be done. But the positioning of those blocks and how those blocks are organized still imparts more information. Some aspects have still been abstracted. If we look then at the programming code example, it gives in text only instructions of what is to occur. But aside from some indenting, there's no real structure other than the instructions themselves. But that programming code is still an abstraction of what's called machine code, or eventually binary code, where it's made up of zeros and ones, where all of those instructions are turned into a series of zeros and ones, which the computer then actually interprets, because it can't interpret anything other than zeros and ones, which we call binary. And that again is part of digital technologies. So understanding that. But the key aspect at the moment is around abstraction. Each of those could do the same thing. They do slightly different things, but in terms of the code, they're the same sort of processes, but they've been abstracted. If you were to be asked to actually program using zeros and ones, and I have done that myself, and it's very laborious and difficult, it's not at all easy, and you're very easy to make mistakes. And if you get 1 0 and 1 wrong, it all goes incorrect and so forth. So we've made commands, textual commands, that represent sequences of zeros and ones. So we can just put those commands in without having to worry about what zeros and ones represent that command. And then block-based programming makes it a little bit easier still. By arranging different shapes and commands within various shapes, we don't have to worry so much around getting semicolons and quotation marks and all of those aspects right that we would have to have correct in textual programming. But even some of the block-based programming can be very difficult for young children who don't quite understand some of the more complex language involved. And so by taking the language out and just using the relationship of shapes, we can abstract it even further for young children to be able to engage with programming. So, abstraction can be used also in design and technology. Here we have students abstracting their designs for a drink machine. Now they can start off with drawing it and sketching it, and then they can increasingly move to more detail by using some CAD diagrams or just rulers and angles and so forth. But they're making more and more detail, but they are still representing abstractions. Now, the big advantage of abstraction and what makes it so powerful, and indeed the concept of abstraction has really driven the information revolution around the use of computers. Computers up till then were just being used for calculations. Human beings could do the same calculations, and indeed were doing it so. They were actually called computers for many years before we actually had digital computers. And they just worked through a whole lot of numerical calculations. But each calculation was specific to a single problem. If I wanted to work out how to get to the moon, I would have to work out all the angles and trajectories and forces and perform the calculations, and I'd be able to work out how to get to the moon. But that solution wouldn't be of any real use for anyone else other than the next person that wants to go to the moon using the exact same rocket and processes. But the idea of generalization is what made computing so powerful. And essentially the very first digital computer was called a general purpose machine. the idea that we could change the problem, change the calculation that was to be performed, and it would then perform a different calculation depending upon what instructions we provided it. But in terms of abstraction, we can now take that generalization further. It provides us with a quick way of solving new problems based upon previously solved problems. So let's say you've written a computer program that moves a little image of a car left and right on a computer screen. So you can make that computer game for a racing car game. Let's say someone else comes along and says, okay, now I want to pay you to make a space game to move a spaceship left and right on the computer screen. Well, that's not that hard now. We can simply change the image from a car to a spaceship. We've got a generalizable solution that we can make some modifications to and be able to use it to solve another problem. And then let's say someone's doing a typing program and they want to be able to move the cursor left and right on the screen. They might be able to use your same code to do that. And then a doctor comes along and wants to be able to have an apparatus move left and right on the patient when they move things on their mouse. And your code could be used in that. And then an automobile maker comes along and says, okay, I need some code to be able to move my actual car left and right on the road, based upon movements of let's hope the steering wheel instead of the mouse in the car. But your generalizable solution might be applicable to that. So you can see how that one little solution to a really specific problem that you may have had can now be generalized and used in a range of different ways. And that's really been the power of computing over the last 50 years. We can take a specific solution and generalize it so it can be applied in many, many other ways, often ways we never even thought possible. So some examples of that you may be familiar with. You've probably all used the Google search engine. The Google search engine, when it was first created, was created over a few weekends in a basement. I think it was just their house, but they created it and it was made out of Lego. Well, the computer was encased in Lego. They couldn't work out, they didn't have a cheaper way of actually making a case for their computer, but it contained the server where people could search for keywords. They could search for some keywords and it would match those keywords against a database that it had in its memory and websites that would link to if those keywords matched items in the database. And let's say we had 100 different items in our database. We might have searched for the keyword education, searched for the keyword crocodiles. And if you put the word crocodile in, it would then find in its database all the different websites that relate to crocodiles and show them on your page. And if you put the word education in, it would find in its database the dozen or so words that related to education and show those websites. Quite a simple solution. If I set that as a problem for you guys, it might take you a week or two to actually make it. But that was what Google was. A very simple problem and a very simple solution. But what has made it into a billion-dollar company is the fact that they realized it could be generalized. So yes, they had a database of 100 search terms and 100 websites that they could match to. But they worked out, okay, what if we allowed 1 million search terms and 1 billion websites and just kept building and building and building? And that's what had led to the success of the Google search engine. Facebook was the same. Originally, Facebook was a program called FaceMash, made by Mark Zuckerberg when he was in college, and he wanted to be able to rank the female students in the dorms in order to work out what who people thought was the most beautiful. A simple problem, showing pairs of images, people chose the one they liked, and it would provide an indication of the most popular girl in the dorms. But what he realized was that fundamental concept of presenting information and having people make comment or share information about that could be expanded upon, could be made more generalized. So that then turned into the Facebook, where people could show their own pictures of themselves or share other people's pictures and show other bits of information about themselves. And that people would be interested in doing that. And not just ranking each other, but leaving comments and sharing information and linking to their friends. And that then turned into the Facebook that we now know today. All because it was generalized from a basic idea that could be then applied in many different ways for many different purposes. Okay, so with that, we then have what's called algorithmic thinking. So going beyond problem thinking, we have a concept called algorithmic thinking. So what is an algorithm? Well, algorithmic thinking involves three different things. The specification of an algorithm, which we talked a little bit about before in problem thinking, what algorithms are, and the implementation of algorithms. So first off, we need to be able to specify those algorithms. And that needs to be specified precisely and clearly so that we can break them down into manageable pieces. As we talked about before, that allows us to decompose our algorithms and allows us also then to abstract and generalize. But algorithms involve a set of instructions, and we need to have those instructions performed accurately. As you saw in the example or the activity we did a few weeks ago around making a sandwich. If the algorithm can be misinterpreted, then it will be. And computers have to follow algorithms exactly. And if we don't understand how the computer is going to follow an algorithm, then it could end up doing things we don't expect and don't want to have happen. So then we implement our algorithms. This involves translating from the algorithm into a programming language. The algorithm is our set of instructions. It can be written just in plain language, plain English. Sometimes we do use diagrams such as flowcharts for that as well, or what's called pseudocode, which is semi-structured English language. But we take that then and we turn it into our block-based programming language or other programming languages. We translate it. And essentially, the implementation of an algorithm, that automation of an algorithm, is what we call computer programming. Sometimes it can also just be a piece of software that does that, but like we can create simple sets of instructions in programs such as Photoshop, which will then change the color and texture and so forth of our images. But in general, it's translating into a programming language. But flowcharts are one way we can use to represent our algorithms. Now, the first aspect of an algorithm is a sequence. We looked at this in week 1 when you used the B-bots. So a sequence is when an algorithm does a sequence of steps one at a time. In this case, a very simple algorithm: cook dinner, eat dinner, clean up. Has a beginning and an end. It goes through that sequence. It's no good cleaning up at the start or eating dinner before you cook it. So it needs to be done in a sequence. Then we have the next aspect of algorithms, which is selections or branching. This is where we can have decisions within our algorithm. So in this case, we leave home, we check the time. Is it before 7 a.m.? If it is, then we take the bus. Of course, we need to, because that will take longer. But if it's after 7 a.m., we're going to be late. We then need to take the subway in order to reach school on time. but there's a range of pathways. And this week in the tutorials, you're going to be, or before the tutorial, you're going to be creating a choose your own adventure computer game, which involves creating pathways in a storytelling way. And the third aspect of algorithms is around what's called iteration or repeating or looping. This is where we create efficiencies by repeating blocks of code. So in this case, we start, we're going to read a value for G. If G is equal to N, then we're going to say we're finished. If it's not equal to N, then we're going to say G is still too small, and we're going to go back and read G again and ask for another number of G. And if it goes through and if it's too big, we also follow a different path in the loop. But it's continuing until the person running the program enters the correct value for G, where G is equal to N. And then the program will stop after it prints done. But it's creating a loop. And in later weeks, we're going to look more detail about how loops can make our problem solving more efficient through that particular structure. Now, there is one other structure called modularity. That's a really fundamental aspect of algorithms, but students in primary school don't tend to use that a lot. So we're not going to explore that. Okay, so this idea of flowcharts. Let's have a look at a contemporary example of this from the TV show The Big Bang Theory.
Algorithm for making friends.
Sheldon, there is no algorithm for making friends.
Hear him out. If he's really onto something, we could open a booth at Comic-Con, make a fortune.
See, my initial approach to Kripke had the same deficiencies as those that plagued Stu the Cockatoo when he was new at the zoo.
Stu the Cockatoo?
Yes, he's new at the zoo.
It's a terrific book. I've distilled its essence into a simple flowchart that will guide me through the process.
Have you thought about putting him in a crate while you're out of the apartment?
Hello, Kripke. Yeah, Sheldon Cooper here. It occurred to me that you hadn't returned any of my calls because I hadn't offered any concrete suggestions for pursuing our friendship. Yeah, perhaps the two of us might share a meal together. Yeah, I see. Well, then perhaps you'd have time for a hot beverage. Popular choices include tea, coffee, cocoa. I see. No, wait, don't hang up yet. But what about a recreational activity? I bet we share some common interests. You tell me an interest of yours. Really? On actual horses? Tell me another interest of yours. Oh, no, I'm sorry. I have no desire to get in the water till I absolutely have to. Tell me another interest of yours.
Uh-oh, he's stuck in an infinite loop.
I can fix it.
It's interesting, but isn't ventriloquism by definition a solo activity? Yeah. Tell me another interest of yours. Is there any chance you like monkeys? Yeah, what is wrong with you? Everybody likes monkeys. Hang on, Kripke. A loop counter and an escape to the least objectionable activity. Howard, that's brilliant. I'm surprised you saw that.
Gee, why can't Sheldon make friends?
All right, Kripke, that last interest strikes me as the least objectionable, and I would like to propose that we do that together. Tomorrow. Yes, I'll pay. All right, goodbye. All right. Time to learn rock climbing.
Okay, so in that example, we used a range of different constructs of algorithms to assist in trying to determine a friendship. And students can use these processes of flowcharting to explore a range of different problems. Now, this represents an algorithm. Translating it into a programming language is then the next step in computing. But an algorithm in itself is part of computational thinking, and algorithmic thinking in particular. Now, this is one that you can try with your own students. So this is a quick way of counting the number of students there are. And I've used it in lecture theatres of several hundred students, where it would take quite a considerable time to count the number of students in any other way. But theoretically, this could be used in a stadium of tens of thousands to relatively quickly identify the number of people in that stadium. So the idea here is everyone starts with the number 1. Then they pair up and they add their 2 numbers together. So both would have then number 2. And one of them sits down and they're now out. And then everyone else then pairs up and they all have the number 2. And so together they add those together and they now have the number 4. And one of them sits down. And then everyone else then pairs up and they both have the number 4, combine, number 8, and one of them sits down. And we keep going until relatively quickly there's only then 2 students left. They add their numbers together and we get the total number of students or people that have been involved in that little algorithm. So this is an example where algorithms can be very powerful. We can use this algorithm, a very simple algorithm, to solve a problem that would be almost impossible in many other ways. If we had an auditorium of 20,000 people and you were given the task of counting them, that would be difficult. You would have to come up with some sort of simplified process for achieving that. And there are often many different algorithms for doing various tasks. And again, throughout the rest of the course, we're going to look at some of those, including what are called sorting algorithms and things of that nature. But we'll explore that in later weeks. Okay, so take another break now and have a look at a computational thinking video that explores how some of these concepts are used with young children. Okay, so our next aspect of computational thinking is data thinking. A huge amount of the power of technology and of digital technologies is how we can actually utilize it to manipulate data. And in fact, really that's almost all digital technology does. There are some ways of doing things without relying upon the use of data, but they are very much in the minority. And certainly the power of data and how we can utilize data is what's provided the success over the last few decades around the internet, and how we can engage with information in ways that beforehand was impossible to do so. So there are 3 main elements of data thinking: data collection, data representation, and data interpretation. So data thinking is essentially how data can be acquired, interpreted, and represented. But this is then used to inform our decision making, which can in turn inform how we then manipulate, store, and communicate information and data through digital systems. So it's what we call recursive. Again, a concept we don't explore in primary school, so we won't go into that, but it's a system that relies upon itself for developing a solution. So the first of these is data acquisition. This is collecting data. And remember, data can be numerical, categorical, or structured in various ways, and it can either be acquired directly or calculated and then used to create information. So having students conduct a survey would be a way of collecting data. setting up a temperature sensor that would measure the temperature over time and have that go into a computer that went then into a spreadsheet automatically would be another way of collecting data. There are a range of different ways of collecting data, but then how we then utilize that data is what's important. But the first thing we need to do in order to be able to utilize it effectively is to be able to present that data in ways that allows it to make sense. Now, as a teacher, you're going to be involved in a lot of data. You collect a huge amount of data on your students, and a lot of effort has been gone into the last decade of assisting teachers being able to cope with the amount of data that is collected, particularly from national assessment tests and external testing that then comes back to schools and to teachers in the form of often numerical data. But being able to turn those into graphs or various forms of symbologies allows us to engage with that data much more easily. A simple aspect for very young children is creating a weekly weather infographic where we put up a picture of a sun if it was sunny that day, or a cloud if it was cloudy that day, or a rainy cloud if it was raining that day. And so over time, we can see the collection of data about the weather through these various symbols that we've utilized. We've just made up the symbols, although they're relatively standardized, but we could have used any other symbol that we assigned the value of a sunny day to. That we need to be able to represent data in various ways so that it can make sense, not just for people, but also for computers. Now, this is where turning data into numbers is actually very powerful. Often in simpler forms of data representation, we take numbers and turn it into other forms, such as infographics and graphs and various images and so forth. But going the other way is also very important. Being able to take that information, excuse me, about the sunny days and the rainy days and the cloudy days, and putting those into numbers so that a 0 represents a sunny day, a 1 represents a cloudy day, and a 2 represents a rainy day, allows us then to do things with that. We could then, for example, come up with an average of the days in terms of the average number of days that it was inclement weather. So data representation is an important aspect. But once we have the data represented, the next step is being able to interpret that data, to use that data to extract meaning. Now, in this image, they're taking data from racing cars. So as the cars are racing around the track, there are data scientists sitting beside the pit crews analyzing huge amounts of data flow from those vehicles, tire pressure, tire heat, oil pressures, huge amounts of information, so that they can make the best decision as to when to have a pit stop, or when the wheels need to be changed, or when something else needs to be done to improve performance to make it optimal. So data can provide us with lots and lots of information about the world that we can then use to make meaning. As a teacher, you're going to use a lot of data to inform your decisions about what to do with your teaching and how to address various student issues and problems and challenges that they may be individually having or collectively having. But students can also use data for a whole range of purposes as well. One simple aspect for young children is looking at the data contained in stories, the number of characters, the number of times a character is happy or sad. And we looked a little bit about that when we looked at simulation modeling. So we can extract a lot of data from a storybook and then use that to analyze what's happened in the story. Okay, so that forms part of computational thinking that allows us then to look at how data interacts with digital systems. Now, these are the internet and the computers and disk drives and flash drives and all the rest. So students don't only need to know about how to collect and represent and manipulate the data and analyze it, they need to also know how it's transmitted and stored and can be worked on using technological devices. And we call these digital systems. And again, we'll be exploring that over the next few weeks. Okay, so another example of thinking about data thinking is that data represents a whole lot of unstructured material. But if we were to sort that data, it then starts making a little bit more sense. We've got various different colors we can now see. Then if we arrange that sorted data, say in stacks, we can see then how many of the different colors we have. And then if we arrange those sorted stacks from shortest to tallest, we can then see more information about those. Which one do we have the most of? Which one do we have the least of? And then if we take that data and we make a story about it and explain the data through storytelling, that provides another level of data thinking. So again, this is enabling students to think about the world in terms of data, that the problems that they face, the challenges, the very world around them is comprised fundamentally of data. And of course, we don't want to just think about data. The world's much richer than just data, but it is also data. And understanding that can empower students, particularly around problem solving. And data is involved in almost all aspects of our lives. There's a huge amount of geographical data, the distances we have to travel, the angle or the direction we have to go to get there, the heights we have to go up and down. There's cultural data, there's scientific data, financial data, statistical data, meteorological data, natural data, transport data, and thousands of others. So every aspect of our world can be broken down and explored as data. And systems thinking allows us to do that in a way that can structure that and look at how that data interrelates. But data thinking allows us to understand that the world is comprised of data. Now, binary is, as I mentioned before, a concept that students need to learn about. Computers are fundamentally dumb. They can only process zeros and ones, which represent electricity being on or off. And the transistors which computers make up are simply that, whether things are turned on or off. And that represents either a 1 or a 0. And that can then be stored and manipulated and processed through. And you would have seen a little bit of that when you did the makey-makey activity, where we can have a signal coming in and we can have multiple signals coming in, and either the signal is either coming in or not coming in, on or off, a 1 or a 0. And how we can make up more complex messages using those 1s and 0s is through a language called binary, where the 1s and 0s can represent a series of 1s and 0s, can represent a number. The number 3 is made up of 2 1s. The number 2 is made up of a 1 and a 0, and a 1 is made up of a 0 and a 1, and so forth. But the letter A is also made up of a sequence of 0s and 1s. Likewise, the letter B, the letter C. And so by doing that and remembering the power of abstraction, by being able to code and write a little program that can code and understand what the letter A means in binary, means we don't have to worry about then that again. We just know A, and we can just use the letter A. We've abstracted that sequence of 0s and 1s so that it's now represented by the letter A. And so we can just use the letter A from now on. Likewise, if we want to use the command print, we don't have to worry about all the binary that's involved in the word P or involved in the process of printing. We simply ascribe that to the word print. And this then abstracts it. So we never have to worry about all the complexity involved when we press the key called print. It's all hidden away. And the advantage of that is that someone else could have written all of that. And indeed, in many cases, they have. And again, we'll be exploring more about that when we look at coding, and how the Scratch programming language in particular does a good job of that, where students can take other students' work and build that into their own program. Again, they're abstracting those elements of someone else's work, and they're now building upon that, just as they're building upon the letter A having been programmed with all the zeros and ones to represent the letter A. But I digress a little. But there are other ways of representing information as well, or representing data. A semaphore system is using flags to represent various letters and numbers. So we can send messages by waving two flags. Very similar to binary, but a different representation system, a different symbology system. Sign language is another representation system where we can use our fingers in our hands to represent numbers and letters. Then we have Braille, again, another system. And indeed our alphabet is another system. The Arabic number system that we use is different to the Roman numeral system, a different symbol system for representing numbers. And of course, different languages have got their own systems. But it doesn't need to just extend to letters and numbers. Images can also be represented with zeros and ones, with symbols. In this case, making little emojis of a smiley face. This is what's called a bitmap, and this is how many of our images are transmitted and displayed on a computer screen. Your computer screen is simply a whole lot of what are called pixels, a big grid of squares, and they're either turned on or off. That's why originally we could only turn them on or off in a single color. And the original computers were either green or orange or sometimes white. But then we had the ability to ascribe to that one single square a range of colors. And so we could then have colored screens. And that's what's called digital TV or digital computer screens. But it's made up of these zeros and ones being turned on or off. And then the intensity and the color are additional bits of information attached to also turning it on or off. So this affects the resolution. The more zeros and ones, the sharper and clearer the image is going to be. And you've probably all purchased digital cameras, and they have a certain number of megapixels, which is how many of those little squares there are in the image. And if there are relatively few, then the image looks blocky. If there are lots and lots, then the image looks very clear and sharp. But it's not just images. We can represent anything, remember, in the world through the use of data. And music is another good example of that. So take another break and have a go at the Chrome Music Lab. This allows you to explore different ways of playing with music through various representations of data and ways of inputting information into a computer to have it display various tones or various images related to those tones. And just another fun way of exploring data, in this case as sound and music. So have a look at that, and then we'll go on and explore our next section. Okay. So our final aspect, we're going to look at computational thinking, although there are other aspects, but keep it simple, we're only looking at four main ones, is evaluative thinking. Now, this is our ability to make evaluations, to make considered critical judgments on evidence that is available. Part of critical thinking. But students need to be able to make two parts of any claims or evaluative claims: a conclusion and an explanation. So they need to make a decision, but they also need to be able to explain their decision, why they chose that or didn't choose that. So evaluation then becomes part of a process that students can use in their problem solving to work out whether or not they have achieved the solution to the specification that was required for it to be a successful solution. So this aspect of evaluative thinking we see in the design cycle, where students specify what is going to be required in their evaluation to judge the solution to be effective or not effective. But it is only one aspect of evaluation. It's an important one, being able to identify whether or not a solution is a good one, if it's fit for purpose. And various properties of our algorithms need to be evaluated as to whether or not they're correct or not. Is it fast enough? Does it give the right answer? Is it economical in the use of resources, particularly time? Now, we often think of computer programs as being really quick and efficient and so forth. But if you've got to say, if you're creating the Google search engine, where you've got to search hundreds of billions of questions every hour, then you want a really efficient algorithm that's doing that. If it takes 1% longer, that could equate to millions of dollars in terms of electricity, just in terms of the processing power and the electric power needed to process that. So there are often trade-offs though between ideal solutions in various situations. And this is where students need to be able to explain their decisions around their evaluations. So often we have in computing, a really specific focus on attention to detail in evaluation. Of course, it can, as I said, mean the difference between a really good solution and a poor solution. For example, let's say you're creating a program that's going to be used to deliver drugs into patients. Now, you want to make pretty sure then that it always delivers the right amount of drugs and does so quickly enough once it's told to do so. If it doesn't, then patients could be in pain or indeed put into danger because of the algorithm that you've written. So you want to make sure that that's a pretty accurate algorithm that's going to work accurately all the time. However, it also needs to be easy to use. If it takes 5 hours to set up, then that's not going to be particularly effective in terms of a solution because the nurses won't have enough time to do that. It also means that they're more likely to make mistakes and so forth. So it needs to be efficient and effective to use, but it also needs to be accurate. And there's likely to be some sort of trade-off between the two. And again, part of evaluation or evaluative thinking is making that decision and being able to justify it, being able to explain, okay, yes, we've made a slider, so you can use the slider to determine how much drug is going to be put in. It's not as accurate as typing in the exact value to 3 decimal points, but it means that the nurse can make the changes really quickly, whereas otherwise they might have to take an hour to reprogram it and or set it up and so forth. So there could be really good reasons why we would accept some loss in accuracy. Obviously not so much that it would be likely to be dangerous, but so that it's actually more performative in terms of its function. Now, another aspect of evaluative thinking is around privacy and security in digital systems, and the protection of student data or any data when it's stored and transmitted through digital systems, again, often involves trade-offs. Yes, we could have a password that you're required to type in 100 letters, 100 characters for your minimum password length. But remembering that is probably going to be rather difficult. So yes, it'd be much more secure, but much less practical and effective. So again, there's going to need to be trade-offs. Yes, we could say we should back up every 2.5 minutes, but that may mean we then slow down our writing speed to half of what it was when we were only backing up every 10 minutes. So again, there needs to be trade-offs and considered decisions. That is a justification that students make in their evaluative thinking that is significant. Okay, so that's computational thinking. In the tutorial this week, what I'd like you to do before the tutorial is to have a go at exploring algorithmic thinking, in particular the idea of different pathways in our algorithms. So I'm going to use a program called Twine, and you're going to create an interactive story. So it's like a computer game, or some of you would have read Choose Your Own Adventure stories, where you read a passage of text and then you're given some options. And then depending on the options, different text is then presented to you. And the story flows along different pathways. Really simple to do. Nice, simple little program. It's all done by just putting in some text and putting some brackets around that text. So for example, you're in a room with two doors. You can either enter the door on the left or the door on the right. And by putting the double brackets around those two options, it will then create additional pathways. And you'll see that graphically in the program. And then I'd like you to use the option to, under Build, which you'll find in the menu, to share to a file, and it will create what's called a HTML file, which is a computer program, a very simple computer program. It's called a web page file. Hypertext Markup Language is its actual full name. But again, we'll be learning about that in a few weeks. But this is just a little file that you can then share onto Teams and into Learning at Griffith, so that your tutors and your colleagues, your other students, can play your story. Then in tutorial, you'll discuss that with your tutor, the idea of algorithmic thinking and how we can abstract various aspects of our story. So for example, making chapter headings is an abstraction. We've taken all the detail of the chapter, summarized it into a heading, and by just looking then at the headings, we can get a reasonable idea of how the story unfolds by just looking at the abstracted heading titles. Or we could go into more concrete detail by expanding out those chapters and reading them in more detail. Okay, the activity then that you're going to do in tutorial is related more to design and technology. And in this activity, you're going to learn about different materials, and in particular, the wonderful world of triangles and how important triangles are in making effective structures. So your challenge is going to make the tallest and most stable tower that you can. And you're going to consider the various materials that you're going to use in making that. Now, for on-campus students, you'll do these in teams, and you'll be using straws and hot glue guns to build the tallest tower that you can make, but it also needs to be strong. Of course, we have earthquake mats that are going to be shaken to represent an earthquake, to see whether or not your tower, while being relatively tall, can survive a reasonable sized earthquake. And a key thing is you can't glue your tower to the floor or to the roof or to anything else. It has to be freestanding. So create your towers and then share those again, or share a video clip or photos of your tower to Teams and to Learning at Griffith. For online students, you'll get a chance to do the same using the glue gun that I asked you to get a few weeks ago and some dried spaghetti to make your own towers. Again, same sort of constraints. You can only use 30 strands of spaghetti, so no more. And if you place your tower then on a piece of paper and wiggle the piece of paper, you can also then replicate an earthquake to see how stable your spaghetti tower is. But the key fundamental aspect of these challenges are that you're looking at the idea of structures and of the materials used to make the structures and how those materials are positioned and connected and organized. And there are some video clips and resources on the website that will help you with that. And as a hint, triangles are your friends. Triangles are a very strong structure when it comes to building things that need to stay together or to be tall and strong. And so utilize triangles wherever you can in the development of your designs. Okay, so that's it for this week on computational thinking. Next week, we're going to be starting the next phase of the course, where we're going to be looking at the more applied aspects of activities that you're going to utilize the theory that we've looked at over the last few weeks and various techniques and activities and tools and approaches in teaching the technologies learning area.